Last time I talked through in some detail the Harris corner detector, which is a way of detecting these key points. Remember, these key or interest points, the terms are interchangeable. These are points that should be reproducible between different viewpoints of the same object. Okay, they're stable points for matching between two images. And then, having detected these points in each of our images independently, we then look at each point independently and cut a little descriptor out of the image based on the pixels local to that point. This is the part I haven't really told you about so far. It's what we're going to use the SIF descriptor for today to do. And then, having extracted all of these local descriptors from all of these key points in all of the images, we get a huge cloud of points, a distribution in what we call feature space. So, for example, as we'll see later, the SIF descriptor, for every one of these key points, it's going to give us a 128-dimensional vector. Okay, it's going to give us a vector for each one of these points, which means that we're going to get a whole cloud of these points in 128-dimensional space. Okay, we're going to then apply this k-means clustering algorithm, which, if you remember, is a way of looking at that feature distribution and performing unsupervised clustering on it to group those points into k groups, what we call clusters, and that's an automatic algorithm based on just the way those points fall, their distribution in that space. Now, each one of those clusters, we're going to treat that as a code word, and we're going to create this frequency histogram here, showing how many times each code word occurs within an image. So, for example, if I were to identify this interest point here, the feature around that, as ultimately falling within code word 1, then that would be, +1 for this bin here in the histogram. Maybe a couple of these landed in code word 2, so we get a couple here on 2, and so on, up to k bins. Okay, so this distribution here shows us how many of each kind of code word there are in an image. Yeah, is that everyone remembering this from last time? Okay, so this is like the digital fingerprint we need to take of this image that shows us the distribution of words in it. Just like when we were looking at the bag of words in text retrieval, I had that page of text, we were counting how often each text word occurred on the page. This is counting how often each visual word, or code word as we call it, occurs in the image. So for every image, we build one of these histograms. Each one of these is a fingerprint of an image. And if you look at the height of the bins in here, you can consider this to be a k-dimensional vector. Yeah, there are k bins, so you could write the heights of those bins out in a big long vector. There'll be a k-dimensional vector, where k is typically 1,000 or 2,000 in a system like this. And then that means your image now boils down to a point in a 1,000-dimensional space, for example. So that's our process of computing that image descriptor. Because remember, in visual search, the process, the magic of visual search, if you like, the process is the process of converting an image to a point in a high-dimensional space. So you can start comparing images for the similarity based on their relative distances in that high-dimensional space, using L2 norm or something like that. Is everyone happy with that pipeline? Yeah? So we're going to be talking a bit more about this today. Okay. So let's just briefly recap on this task of unsupervised clustering, this process of k-means clustering that we perform as part of that bag of visual words pipeline. If you remember, this problem of unsupervised clustering is, given a distribution of data and very little knowledge about that data other than just its distribution in the space, group that data in some way. And in the case of k-means clustering, we're actually faced with what we call a semi-supervised problem, because we do tell the algorithm how many clusters should exist in that data, we just don't tell the algorithm how to find those clusters. So I stepped through, and I won't go through this in detail because we did it last time, but just as a recap, we stepped through this k-means clustering algorithm last time. The idea is, if I have a distribution of data, which is indicated here by these green points, and I wanted to group that data into two groups, using nothing more than its distribution in this space, then I could run my k-means clustering algorithm, setting the number of clusters or groups that I want to be 2. So we say k equals 2. The first step in that algorithm is to pick 2 points in that space that are random. It doesn't have to be data points, just 2 random points in that space. We're going to show those as the red and the blue clusters here. And then what we're going to do is just do what we call nearest neighbour assignment. We're going to look at every data point and figure out which cluster center, red or blue, that point is closest to. Okay, having made that assignment there, and I've shown it here with the colouring, the shading there of those data points, they've gone from green to red and blue there, and we then calculate a new mean of the red points and a new mean, that is average position, of the blue points, and those cluster centres are updated to be that new mean. And we just simply repeat that process then from step 2, just making that assignment again based on nearest neighbour and calculating those new means iteratively until the means they don't move anymore. We say the system has converged, or we hit some ceiling on the number of iterations we're willing to run this algorithm for. And at that point then, our points have been associated to one of the two clusters. Each point has been associated to one of the two clusters. That's this k-means clustering algorithm. Everyone happy with that? So that was that algorithm that we were performing there in our bag of visual words. So that big cloud of feature points here in the feature space. Yeah.
Say you reach a point where it's constantly switching, just like there's one stop moving across each way.
Yeah.
Is it better to reach a certain number of iterations where you call it quits, or is it better to have a bias and say that if it does this, to have this kind of equidistant behavior bias toward one side?
Yeah, I mean, from a practical point of view, it doesn't really matter if that sort of situation occurs. So, yeah. Honestly, I've got a colleague in CBSSP who did quite a lot of experiments in the bag of visual words stuff a few years ago, and he kind of came to the conclusion that actually it doesn't matter even if you only run the k-means just for a couple of iterations, as long as some kind of grouping of these feature points occurs, it's kind of good enough. It doesn't really matter if it's a good grouping or not. So you get about like a 1% performance accuracy boost if you kind of run the iterations for a very large number of times. So honestly, I can see why you're asking the question, but really it doesn't really make an awful lot of difference. Right, okay, and when we saw the outcomes of that. So yeah, as I say, today, the point of most of this first hour is to discuss this process then of computing features local to each of these interest points, which, as I say, could have been identified using something like the Harris interest point detector. To do that, we're going to look at this thing called SIFT. SIFT stands for Scale Invariant Feature Transform, and it's a way of extracting descriptors local to those interest points that are what we call affine invariant. So I introduced this term last time. Affine invariant means we should get the same response from the algorithm regardless of whether the image has been translated. That means the content in the image has been shifted around. The rotation of the image, so the orientation we view the image from, and also the scale. So in practical terms, that would be the distance of the object from the camera. If any of these things change, then what we'd expect to do is get the same descriptor local to those interest points. So, for example, if we had a picture of this book here, okay, and here, these are clearly subject to affine variation. They've been translated, rotated, and scaled, but we would still end up somehow extracting the same fingerprint from both of those regions, and therefore the system would be invariant to these affine transformations. So how do we do that? So we're going to use the SIFT algorithm. So SIFT is actually it was something that was introduced in 2004, so some time ago now, by David Lowe and his student Matt Brown at Canadian University, and basically it's actually two algorithms in one. It comprises what we call a detector, which is a way of finding interest points, and a descriptor, which is a way of describing the interest points. Okay. Now, in the lecture today and in this module, we're not going to focus in too much detail on the detector. We're just going to focus on the descriptor. You can consider, the Harris corner detector would be one way of doing the detection potentially. Let me just very briefly summarise how the detector works, just for your interest, but it's not something I think we need to really dwell on. The idea of using SIFT, the detector part of the algorithm, is again, because it's more robust than the Harris corner detector in terms of it being not only translation invariant, but also scale and not only translation and rotation invariant, but also scale invariant as well. And it's the first time we've encountered this idea of processing images in what we call scale space. So usually in computer vision, when we want to analyze an image, it's often useful to analyze an image at what we call different spatial scales. So imagine that I took a photo of this room, and I blurred the image really heavily, okay, I'd probably still be able to see the door and the wall here, but perhaps I wouldn't be able to see the details like the bricks on the wall or the light switch or something like that. So, by blurring the image really heavily, I would pick out objects of a certain spatial scale. And maybe if I blur the image less, then finer grain objects like that clock on the wall or the light switch might turn up in the image, okay. So clearly the level at which I blur or low pass filter more accurately an image defines the scale of artifact that's going to be present for analysis in that image. Okay. So the SIFT algorithm for detecting key points, as I say, it's like an alternative to Harris, performs this scale space analysis on an image by taking the input image and blurring it to various different degrees. In fact, it blurs the image with a kernel that's 2 times, 4 times, 8 times some constant amount. That means we process the image at what we call octave power intervals. The basic idea is to blur the image at these different levels of scale, and then compute the difference between adjacent scales of the image. Now, when we blur an image at progressively coarse scales, we have a special term for that in computer vision. We call it computing a low-pass pyramid of the image. Okay, and when we difference adjacent levels of the low-pass pyramid, we call that a bandpass pyramid. Okay, now what's happening when we difference two adjacent layers in an image? In a low-pass pyramid, is we're calculating the difference between artifacts at one scale and another, and it's equivalent to having convolved that image with a difference of Gaussian. In other words, selecting a certain band of frequencies that we're interested in. So if we look at adjacent differences between adjacent levels in this pyramid, what we're actually doing is looking at artifacts that exist at different frequency bands in the image. In other words, at different scales in the image. Okay, so basically the SIFT detector creates this bandpass pyramid, and then it looks at particular levels in the bandpass pyramid. For example, this is one layer in the bandpass pyramid. And it looks for local points of minima and maximum brightness in that image. So if you remember the way the Harris corner detector worked, it swept a window over the image, okay, and it looked for points within that window that are it looked for windows where the point in the middle of the window was brighter than or darker than all of the surrounding pixels. In other words, was the local minima or local maxima. SIFT detector algorithm does the same, but in fact it looks at the bandpass pyramid, and instead of looking at a window within a single layer of the bandpass pyramid, it actually looks at a small 3x3 volume. So it's looking for local minima not only with respect to the surrounding pixels in the current layer, but also the layer above and the layer below in the bandpass pyramid. Does that make sense? Anyway, this is really more for kind of a point of interest for this lecture. It's not something we're going to dwell on. We actually talk about the SIFT detector algorithm a lot more in the master's module around deep learning. But in any case, it's a way of detecting these key points. And what you actually get when you detect a key point, which is one of these maxima or minima, is you get not only an X and a Y location for that maxima or minima, but you also get to know which level in the pyramid it existed at, okay? In other words, which scale it existed at. So what you can do then is, having detected these points, you can establish a window local to that detected point, the scale of which, the size of which, is determined by the level of the bandpass pyramid that you detected that minima or maxima at. Does that make sense? So if I detected, for example, this feature here, this maxima at a very coarse level of the pyramid, that means that maxima corresponds to a very large object, okay? It has a coarse spatial scale. So the window should be that much larger in order to capture that artifact. Does that make sense? Okay. So the SIFT detector then is a way of detecting these interest points, just an alternative to the Harris corner detector. It gives us not only an XY location, but also a scale for those points. The other thing that we can do is compute an optimal orientation for that window in order to sample the texture about that point as well. So we've got the window size, we now need to figure out its orientation. How do we do that? Well, if we were to sample just using a regular rectilinear window, aligned with the image about that point, and then look at the pattern of intensities within there, we could determine the direction of principal variation of those intensities. Yeah? This is actually what we do when we perform the Harris corner detector algorithm. If you remember, we have a window and we calculate that covariance matrix, so all the steps I went through last time. And by looking at the direction of the principal eigenvector, we know which direction the grayscale values are changing the most in. Yeah? Are varying the most in. Well, we do the same exactly the same thing here. I mean, this is, as I say, a generalization of the Harris corner detector. So by detecting the direction of principal variation of the intensities within this window, we can figure out which direction the principal eigenvector is pointing in, and then we can rotate that content so that principal eigenvector is always pointing along one of the axes, along the y-axis, for example. And that then allows us to cut that window, align it, and then extract features that will be little patches of texture that will be the same regardless of the orientation of this image. Yeah? In other words, if I took this image here and I just rotated it some arbitrary angle, okay, I'd end up detecting the same maximum minimum in it, the same key point at the same scale, but that window would be aligned in a totally different direction, and we could reorient it back to the vertical again by just watching for the direction of principal variation and normalizing against that direction. Does that make sense? Okay. Anyway, in any case, the bottom line with a sieve detector is it's a way of computing this window local to interest points that are detected. And then the real question of interest today is how do we extract then, having detected that key point, how do we extract a local descriptor from that window? Okay. So the way that we do that using the SIFT algorithm is basically to compute something very similar to the edge orientation histogram that I went through in lecture 7 and that you're probably busy implementing already for your coursework. If you remember, the idea of edge orientation histogram is to produce a frequency histogram where we have basically the full 360 degrees, or 0 to 2 pi radians if you prefer radians. It's been broken up into 8 intervals, so 45-degree intervals. And what we're doing is counting up how many times the edge orientation is pointing in each of those bins, if you like, 45-degree bins. So what we do is we take our window of pixels and we actually slice it up into a 16 by 16 cell grid. Okay, and then within each of these grid cells, as I say, exactly just like the visual search lecture I gave you on edge orientation histogram, we calculate the average orientation of pixels within that cell and quantize it to the closest 45-degree bin in order to create this frequency histogram for the orientations of the edges. Does that make sense? Does everyone remember the edge orientation histogram from last time? Yeah? Ask me if you don't. That's fine, I don't mind saying it again. Okay, so what we've done then is we've taken our little window that we've extracted local to our key points. We've established a 16 by 16 grid around it, and then we have we've computed this histogram within it. Okay, so in actual fact, what we do is so to be more specific now, so we take this 16 by 16 grid, we actually break it up into a 4 by 4. So we group these cells into 4 by 4 groupings. So we got a 2 by 2 cell, 2 by 2 cell. So we got 16 groups, and then for each of those groups we calculate the histogram. So what we end up with is 16 groupings, each of which we have an 8-dimensional histogram for, and then we from that derive our 16 times 8, which gives us 128 values, which is our 128-dimensional descriptor that comes out of the SIFT algorithm. So, I don't know how clear I was with that, so I'll say it one final time. Given a window that's been output by the detector, we establish the 16 by 16 grid over it, and we average within each of these cells the edge orientation. We then group those to create further averages, 16 of them, which we quantize to create this histogram. Yeah? Okay. And then the final thing that we do is when we're creating this histogram, we downweight the contribution to the histogram if the cells are further away from the center of this window. So, for example, these cells here will contribute large values to this histogram. As we move further out, like this cell here, this 2 by 2 cell here, will contribute less to the histogram. Does that make sense? It's like trying to kind of foveate or add a bias towards the center of the region. Right, so there we go. There's our 4 by 4 grid of 2 by 2 cells. That's probably a clearer slide than the previous one. Okay, so how well does this SIFT detector and descriptor perform? Well, this is one of the figures from that original paper from David Lowe in 2004. You can see what's been done here is we've taken an image of this comic book and we've detected SIFT features, and we've extracted the SIFT descriptors local to each of those features around the from this image, and then we've done the same here in this image here on the right hand side, and using a mechanism for matching those SIFT points, which I haven't got into but we'll do in a couple of slides time, we've been able to establish what we call correspondence between those two images. And you can see that the SIFT descriptor, despite there being some occlusion and clearly some affine transformation of that image in terms of it having been rotated, scaled and translated, you can still see there's quite a substantial number of matches have still been able to be picked up between those two images there. And based on the analysis in the paper, it turns out that this algorithm is robust to about 60 degrees of viewpoint change, a scale factor of either 0.5 or 2, depending on which way you scale, and partially robust also to illumination change. Why do you think the descriptor that is being computed from the local to each of these key points is robust to illumination change? How is that histogram being computed? What data is being used to compute that histogram? Yeah, gradients in the image. Yes, it's an edge orientation histogram. We're looking at the direction of edge orientations to compute it. And we get that, of course, as we discussed in lecture 7 for visual search, by convolving the image with something like the Sabel filters to produce a first derivative to identify the gradients in the image. So if I have an image here and I dim it down, if I reduce the brightness of this image, I'm still going to get the same edge orientations here. It's just the brightness of the image will be reduced, right? So because the descriptor has been computed from this first derivative information, it's robust to illumination change. We say partially robust because, of course, if you like dim the image to completely black, it wouldn't be any good at all. Okay, but I mean, it is pretty robust to a rotation change, to illumination change. Yeah.
What else do you want to change that? Rotating this way or?
Yeah, that's a good question. So, okay, the question is, what is viewpoint change? Well, okay, when we talk about affine variation of an image, we talk about translation of the image. So, if you had a photo of this bit of paper here, I'm translating it now. I'm scaling it by moving it further away or towards you, and I'm rotating it, but I'm rotating it in line with the optical axis of the canvas. I'm rotating it like this. If I'm tilting the image towards you or away from you, we call that out of plane rotation. So in actual fact, out of plane rotation, as we'll discuss later on the course, isn't really an affine transformation. It's what we call a projective transformation. Okay, so nevertheless, it's kind of robust to that too, but they don't quantify how much in the paper. Yeah. Yeah, for in-plane rotation, so rotation on. Well, I mean, it degrades gracefully, but if you go beyond 60 degrees, it tends to not work so well. So that was the conclusion in the paper. That's what I'm trying to communicate. Yeah. You can read the paper for more analysis, but yeah, I'm giving you the sort of operational characteristics of the algorithm. Okay, so then just plugging that in then into this framework then, just referring back to bag of visual words, the process then is to detect these key points, we would run some form of interest point detector, which would be either the Harris corner detector or the SIFT detector potentially, although we haven't gone into too much detail on how the SIFT detector works on this course. And then we local to those interest points, extract from a window local to each of those points the SIFT descriptor, okay, which is this kind of generalization of the edge orientation histogram. And that then gives us our cloud of points then, our distribution of points in 128 dimensional space, which we cluster and ultimately use to compile this frequency histogram. So is everyone clear on how this pipeline works? Ultimately, it's a way of converting this image into this frequency histogram and therefore a point in a k-dimensional space. Okay, so we've seen then how this bag of visual words pipeline can be used for image search, for visual search, but we're going to look at some other applications of SIFT and bag of words in the remainder of this hour. As I showed you with that example of the comic book, one of the other major applications of SIFT is to create correspondences between sparse points detected in a pair of images. So this is often used in applications like Photoshop or other photo stitching applications where you want to create a panorama, as it's called, a mosaic of two images to stitch them seamlessly together. So in this example here, I've taken two images of this library, which is I think the library at Bath when I used to work there, and in fact, and I've detected Harris corners in each of these images, and then computed the SIFT descriptors local to those Harris corners, and established correspondence between those SIFT descriptors in some way, the way I'm about to tell you. Okay, so the red and the green here correspond to Harris corners that have been detected in in each of the images respectively. It looks blurry because I've overlaid the two images on top of one another, so you can see that there is quite a change in viewpoint on the two images. And the blue lines are connecting corresponding points together. And then, having established those correspondences, it is possible to warp one image onto the other, to warp those corresponding points onto one another. We don't talk too much about the warping process here, so we're talking more about the SIF matching process. So how do we go about matching these SIF points? Well, as I say, when we run this interest point detector, what you've got is a collection of sparse points on each of the images. And of course, local to those sparse key points, you've also extracted these SIF descriptors. So effectively, you've got two clouds or a distribution of points within this 128-dimensional space, the SIF descriptor space. The process then for establishing correspondence between SIF descriptors is to look for points within this 128-dimensional space that are close by. So, for example, this red point and this green point here, these are SIF descriptors that have been sampled from each image that are close by within the descriptor space and therefore code for very similar content in the images. It would be reasonable to consider these 2 points as being corresponding. So when we detect point correspondences between the images, we're not using the XY locations of these points in any way, the location of the points in the image. We're using the location of the points within the 128-dimensional descriptor space. Does everyone see that? So the process for establishing correspondence then between two images is to start with one image. Let's say we start from this image here on the bottom here, this red one, and we say, okay, for every point in here, let's start with this one, say, we're going to look at every green point, every SIF point in the other image, and figure out which one is closest to that point. So in this case, it would be this green point here. And then we're going to say, okay, well that is a correspondence then. Okay? And then we're going to look at the next red point in that second image there, and then figure out which of the green points is closest to that, and so on and so on. And we go on assigning these points with replacements. So it's quite possible that a red point could end up the 2 red points could end up corresponding to 1 green point. Yeah? But then we end up matching in the other direction. We go through every green point and we look to see which of the red points is the closest. So we're running the correspondence now in the opposite direction. Yes, everyone follow? And we keep on doing that for all of the points. And what we're going to do is only keep as possible matches points that uniquely map from one to another, have what we call a bijection. So in this case, for example, this red point maps to this green point as its closest neighbour. But then having done the search with this green point, we found this red point to be its closest neighbour as well. So those points uniquely map to one another, so we keep that as a valid correspondence. But there will certainly be situations where, for example, you might be looking, starting with this green point, you might say, okay, find me the closest red point. Oh, it's this one. So I'm going to have this match. But then, if I were then iterating through the red points, I might match this red point to this green point, but then I might match this red point to this green point as well. So that's no longer a unique match. So that would be no good. We just discard all of that as a possible correspondence. So having filtered to ensure that these matches are kind of two-way matches, what we also do is we look for the second closest match. So it might be the case, for example, that if I were to match, let me pick another example on here, or let's say I pick, I'm looking at this green point here, and I find this to be the closest red point, and this to be the second closest red point, okay? Because these distances are pretty similar, there's quite a lot of ambiguity as to whether, really this is the best match, or whether this is the best match. But there will be other situations, for example, like this one here, this green point, this is clearly the closest match, but the second closest red point is quite far away. In fact, it's greater than a certain scale factor, typically we choose 1.4. So this is a great match then, because it shows not only has it got a bijection, is it a two-way match, but also the second closest match is considerably further away than the closest match. So there's very little ambiguity there. So we keep that as a good correspondence. So actually, although we start off creating a good deal of correspondences between the two images, we only end up retaining only a small number of correspondences as stable matches. And these are the matches here that have been shown here by these blue lines. Does that make sense? Yeah? Any questions on that at all? All right. So that application then, we'll come back to this slide later in the course, because what we end up getting then for these two images is points that correspond between reproducible interest points between the two images. So in this case, between that pair of images, we might have visualized here maybe around 20 of these corresponding points. It's possible to calculate a warping transform then using those 20 corresponding points. In fact, you actually only need 4 corresponding points. You can calculate a unique warp that will warp one of those images on top of the other in order to create a seamless stitching of the two images together. It's what we call a homography. We're going to talk a lot more about homographies later in the course, but for now, we just need to know that it's quite a useful process to be able to match these SIF points in order to produce sparse correspondences between images. Okay, so we've talked a little bit about the bag of visual words pipeline for visual search and how we can boil down an image to being just a point in a high-dimensional space, in this case a k-dimensional space, using that histogram. But there are other applications of bag of visual words as well. In fact, we can also use it for object recognition. So, if we were to look at the problem of object recognition, again, what we want to do is take an image and extract from that image some digital fingerprint, some point in a high-dimensional space. And if we use the bag of visual words pipeline to do that, then what we're going to get is a point in a k-dimensional space for every image. Now, because this bag of visual words framework is encoding basically distributions of different visual words, different kinds of texture that are present in each of these images, it's reasonable to assume, and in fact it's the case, that images that contain similar objects, which in turn contain similar distributions of structure and texture, will end up mapping to similar points in the high-dimensional space. So, for example, cows might all map to this region in the high-dimensional space, but planes might map to a different region, and cars might map to another region. So one way that we can perform object recognition then, the process of figuring out, what object is present in an image, is to take every image and run it through this bag of visual words pipeline in order to create these clusters. And what we might choose to do, similar to our, thinking back to week 2, our supervised classification for our sky classifier, do you remember we built an eigenmodel, in order to model the statistical distribution of a cluster of points? Well, what we could do is build an eigenmodel over each of these 3, in this example, classes of points. So let's suppose that I build 3 eigenmodels here. This one here over the distribution of red points, the cow points. This eigenmodel here over this distribution for planes, and this here for this distribution of cars. If I then take a query point, a new image, and I want to know what that image is, that's the blue point there with the car and then the question mark next to it, I want to know, is that a car, is it a cow, is it a plane? Well, I can just push that image through the bag of visual words pipeline to get a point for that image, that query image, in the high dimensional space. And now I can just measure the Mahalanobis distance of that point to each of those 3 eigenmodels. The minimum Mahalanobis distance, in other words, the eigenmodel that's closest to that query point, is going to be the class of that point. Yeah? Does that make sense? So this is another great example, and we keep coming back to it, of using the eigenmodels, this principal component analysis, in order to classify signals in some way. In this case, the signal is present in this k-dimensional space. It's a representation that allows us to take an image and just map it to a point in the space. We've seen that's useful for visual search. But if we use eigenmodels in this space, we can see we also use the same pipeline for object recognition. Yeah?
Is one of those points represent an entire image?
That's exactly right. One of those points does represent a whole image. Yeah.
How do you manage to summarize everything?
Well, okay, so the question is, how do we summarize an image into a point? Well, that is what the bag of visual words pipeline does. Okay, so maybe I should just go through that pipeline one final time. The process for summarizing this image to a point in that k-dimensional space is as follows. We take the image, okay, we detect interest points in it. For each of those interest points, we calculate the SIFT descriptor from the window of points local to those points. That gives us a whole bunch of sparse features, that is, features that have been computed local to each of those interest points. Okay, we then look to see which code words those features fall into within this dictionary that we built, this k-means clustering that we built over our training set. Okay, that enables us to build this frequency histogram, which is just simply a count of how many times each code word occurs in this image. So let's suppose that this interest point ends up mapping through to 1. This interest point maps to 2. This interest point maps to 2. This one maps to 2. This one maps to 5. This one maps to 10. Okay? And then we count it up, and that gives us one histogram for the image. Yeah? No. So that histogram is one histogram for that image. Another image will give me another histogram. So that histogram here is a bunch of numbers, which is the heights of those bins. So write out all those numbers in a big long vector. It's got k entries in it. That is a point then in a k-dimensional space. So that is transform that image to a point in a k-dimensional space. So that's how we've gone from one image to one point, which was your question. Does that make sense?
Yeah.
Okay. Yeah, so the whole point of the bag of visual words, so histograms have been used twice here. They've been used within each computation of the SIF feature to compute where this lands in the 128 dimensional space. And then it's used here at the end to count up the code words presence. Yeah? So it's used in two places. The whole point of the bag of visual words pipeline is the conversion of this image to a point in a k-dimensional space. Any other questions? Okay. So, and other useful things we can do with this, having established a classification for our query points, what we can also do is look at the ratio of the Mahalanobis distances. So, if that point here is pretty much, 3 from every cluster, then we haven't really got a very clear decision. In other words, that point is quite close to the decision boundary in that space. We haven't got a very clear decision as to what class that point should be. But if one of these Mahalanobis distances is much smaller than the others, then we can be pretty confident about its classification. So we could use the ratio of those Mahalanobis distances to give us a confidence, as well as looking for the smallest one. We could look at their relative values. Okay. I'm going to touch very briefly on another kind of classifier called a support vector machine. Okay. In fact, if you're doing the advanced signal processing course, you'll spend about a third of that course talking about support vector machines. So I'm not going to go into them in any detail beyond sort of how they can be applied. Specifically, I'm not going to go into how we train them. So a support vector machine is an alternative classifier to an eigenmodel that actually gets used a lot more in practice. It's a high performance classifier. In its most basic form, it is a two-class classifier. Remember, we have a special word for that. It's dichotomizer. The whole point of a support vector machine is to figure out the decision boundary in a high-dimensional space that separates two categories of points. So suppose I took that previous example. It had three categories. Let's forget about the cars. Now I've just got planes and cows. Okay, they're my two categories. So what I'd like to do is define a dividing line, a special name for that, we call it the support vector, that is basically the best decision boundary we can come up with to separate those two categories. Now this is a high-dimensional space, so actually that line I've just described is not a line at all. It's actually like a surface, a plane. We call a hyperplane if it exists in dimensions higher than 3, that divides those two clouds of points. So, right, I think we'd all agree that that would be a bad choice, right, of support vector. Yeah? Right, because it doesn't divide the two categories up. It's not a very good decision boundary. Right, this would be a better choice of support vector. Yeah? But how can we define quantitatively what the best support vector is that separates these two classes? Well, the best support vector is the support vector or decision boundary that maximizes what we call the margin between the two categories. Okay, so the margin is calculated by looking at the closest point in each category to the support vector and looking at the distance it is from that support vector. So the margin on this side here is shown in purple, margin on this side is the other purple line. And their separation is, well, actually that is the quantity that is called the margin. And what we're looking for is the maximum margin between the categories. So that's not a bad choice of support vector, but this would be a better choice because it has the maximum margin between the two categories. Yeah? So there is, as I say, a process for training these support vector machines to find this margin. It involves solving a quadratic programming problem. It's something that's covered, well, there's no way I could cover it in a lecture, put it that way, but there's another module that covers that. So we just treat that as a black box for now. But assuming that we found that support vector, there's a quick and easy way to figure out, given a new point, which might be my query point, which side of the support vector it's on, okay, which category it belongs to. And the way that we do that is by calculating the dot product of that point with a vector that is perpendicular to the support vector. And that is a vector quantity now. So remember, that support vector is like a hyperplane slicing between the two categories in the high dimensional space. And the vector that is normal to it, okay, perpendicular to it, is this vector A here. Now, if I've got my point B in this space, and I calculate the dot product between A and B, that gives me a number, okay, a scalar value. And what I'm looking at is the sign of that value, whether it's positive or negative. Why am I looking at that? Because hopefully everyone knows this relationship. A dotted by B, the dot product of A and B, is equal to the magnitude of A, the length of a vector A, multiplied by the length of vector B, multiplied by the cosine of theta, where theta is the angle between those two vectors. Okay, now if we look at where this point is here, this is on the green side of the support vector. Okay, on this I think we call this category 2. So we can see that any of the values basically within this section here of the space are going to be in the range theta 0 up to theta is 90 degrees. Yeah? Then if I'm on this red side, category 1 of the space, then I'm going to be in the range theta 90 to 270 degrees, and then in this region I'm going to be 270 to 360 degrees. So if I look at a plot of the cosine curve, regular cosine curve, you can see that that also follows the same, changes. It's positive within the first 90 degrees, negative within the second and third next 90 degree sections of the range, and then positive again for the final 90 degree of the range. So by looking then at just the side of this dot product, you can see it's a reliable indicator then as to which side of the support vector this point lies on. So this is just a technique you often see in textbooks and papers that people use support vector machines for their classifiers. And this is a very simple kind of support vector machine for two reasons. First of all, the support vector is linear. So sometimes we call it a linear support vector machine, or just linear SVM for short. It is possible to create what we call non-linear support vector machines, but we're not going to go into that on this course. It involves some trick called kernel trick you do around the dot product, but it's not of interest on this course. And the other reason that it's a weak representation is we're only looking at 2 classes here. But actually, we can generalize this idea to any number of categories, yeah?
What if there's more than 2 dimensions? How can we call it?
Well, yeah, so theta is defined by this dot product, okay? So in this example, in fact, there are more than 2 dimensions. So the support vector is not actually a vector at all. It is a hyperplane, it's the decision boundary in the high-dimensional space. So, but vector A is always a vector because it's the normal to that hyperplane, yeah? So therefore, it's always possible to calculate the dot product between A and B, and therefore get a sign of A dotted by B, yeah? So, is that a question? No. Okay, so how do we generalize this idea to more than 2 categories? Well, there are several ways of doing this. One way is using a one versus one technique, as it's called. So in this case, what we do is we look at all the possible combinations of pairs of categories. So, for example, if we ignored the presence of categories 3 and 4 in this diagram and just treated this as a dichotomizer, a classifier between category 1 and 2, we could train up an SVM just to tell the difference between category 1 and category 2 using this pipeline I've just outlined. And then we could test our test point using that dot product. We could also create an SVM to tell the difference between category 1 and category 3, and also between 3 and 4, and also between 2 and 4 and 2 and 3. All the combinations. And having trained up that whole bank of these SVMs, then what we can do is take a test point and run it through, test it against each of those SVMs to see, which category is the winner for each context. So this would be our SVM we train to tell the difference between category 1 and 2. We put our test point in, we see that ends up being category 1. If we try between 1 and 3, ends up in category 1, and so on. And then we look down this column here to see basically which categories are won the most times in these comparisons, and that is a way then of generalizing our SVMs to work over more categories. There are also other schemes called one versus all and things like this. We won't go into them on this course. So really I just wanted to end this hour by just noting to you that although we focus primarily upon the eigenmodel as a classifier on this particular module, in practice people tend to use other kinds of classifiers too, like support vector machines. So in summary then, this hour, we've basically delved down a little bit deeper into this bag of visual words pipeline. We've talked about how it can be applied not only to visual search, but also to the problem of object recognition as well. We've seen that the bag of visual words pipeline involves detecting key points using either the Harris key point detector or corner detector, and also the SIFT detector is another alternative. In any case, it involves detecting these interest points and computing a descriptor local to each of those points using the SIFT descriptor. We've looked at the SIFT descriptor in some detail. Then we saw how those SIFT descriptors are clustered using k-means, used to produce that k-binned histogram, ultimately mapping an image into a point in a k-dimensional space. We've seen, as I say, that applied to visual search and object recognition. We also saw another application of the SIFT descriptor to matching sparse points between a pair of images, which is also used for things like image stitching for panoramas. And there's more detail on this within the course text, these two chapters. Right, okay, well let's leave it there for the first hour, and we'll have a break until 3 o'clock. So, thank you.